All right, so today we're going to learn about how to graph a polynomial by hand. So without the aid of a graphing calculator or Desmos or some online tool. So this is going to be covering section 3.4 in our pre-calculus textbook, right? Now, pause, copy this down, and then I'm going to fill in some spots here, okay? All right, we're looking at graphing a polynomial. If you recall, that's a function of the form f of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus dot 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 dot, an a sub 2 x squared, an a sub 1 x plus an a sub 0. The a's are just real numbers, and then the x's are our variable. And if you recall, we call a sub n times x to the n our leading term. Okay? And this polynomial has degree n because that is the highest power of x that the polynomial has. The steps to graphing a polynomial are not too long. It's 4 steps plus the 5th one where we sort of put it all together. First step is to determine the y-intercept, sorry, that should be singular, the y-intercept of the graph. And all we do is we compute, to figure out the y-intercept, we compute the y value when our x input is 0. F of 0 is our y-intercept. Great. The next thing we determine is the end behavior of the graph. Now, from our previous work, we know the end behavior of a polynomial depends entirely on that leading term. So we're going to ask the questions as x approaches negative infinity, what does that leading term a sub n times x to the n power approach? Does it approach positive infinity or does it approach negative infinity? And then we'll ask the same question as x approaches positive infinity. What does that leading term approach? All right. So this will help us determine what does the graph do way off to the left as x's go down to negative infinity and way off to the right as the x's head up to positive infinity, right? Okay, we then look to determine any and all of the x-intercepts. To do this, we're going to set our polynomial, which I'll be a bit lazy about writing. We're going to set our polynomial equal to 0 and solve for x. And the way we're going to solve for x usually is to factor that polynomial, usually via factoring. Okay. All right. And then the last step before we put it all together is this new notion of determining the multiplicities of the x-intercepts that we've just found. And I'll talk us through that when we do the one example in this video. Okay. This is going to help us determine what the graph looks like when it crosses or when it hits the x-axis. All right. Okay, well, once we have all that, y-intercepts and behavior, x-intercepts, and the how the graph looks at the x-intercepts, we're going to put all that information on the graph and sort of connect the information into a coherent looking graph. Okay. All right, so we're going to go over and start the example then. All right. Now, the setup here is I've got the problem stated up there, and then those same 4 steps that were on the previous panel are on the board behind me. And here's where the graph will ultimately go. So why don't you at least pause and copy down what's on this board here, and then I'll start talking us through the solutions. All right, and I'm going to do my graph in red. As I get information, I'm going to put it on the graph. First step, the y-intercept. This is a great warm-up since it's fun and easy. So I'm going to compute f of 0 And if I plug 0 in for x, I see that I just get a 0 coming out. So y equals 0 is my y-intercept. All right, cool. So my graph will cross the y-axis at y equals 0. So let me put that dot there. I find it easier to do one step, put the information on the graph, do the other step, put the information on the graph, et cetera, right? Okay, end behaviors. I look at the leading term of my polynomial, the term with the highest power of x. So that's the x cubed term. So leading term is 1 times x cubed. Okay, if there's a number next to the x cubed, that's part of my leading term. Okay. All right. Now I ask the question. As x approaches negative infinity, let's figure out what 1 times x cubed does. 1 times a big negative cubed. Well, if I have a big negative number, and again, I'm thinking like -1,000, -1,000,000, if I cube that, it's still huge. It's even huger now, and it's still negative. So that is still a big negative. Okay. All right. So it looks like as x goes way off to the left, my leading term heads way down to negative infinity. So I'm thinking 1x cubed is heading to negative infinity. All right. And let me put that information up on the graph. As x heads way off to negative infinity, my outputs dictated by that leading term is heading way down to negative infinity. So roughly speaking, I'm having that behavior to my graph, way off to the left. The graph is heading down, 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 and keeps going down to negative infinity. All right, well, same story then for way off to the right. So as x approaches positive infinity, let's see, 1x cubed, I'm thinking of that as 1 times, I'm going to replace x with some big positive number, like 1,000, 1,000,000, 1,000,000,000, and the leading term says to cube it. All right, well, if I have a big positive number and I cube it, it's even bigger, and it's still positive. So I'm getting something big and positive coming out. All right, well, that means it's heading up to positive infinity. So 1 times x cubed is heading up to positive infinity. And let me translate that to my graph. As my x values head way off to the right, my outputs dictated by the leading term is getting really big. So I'm seeing something like that happening way off to the right, right? So I got a little bit of information in the middle. I've got information on the edges, and I can go on to step 3, the x-intercepts. Now, we'll often refer to the x-intercepts as the zeros of a function. All right, well, let's do the work though. For the x-intercepts, I set my polynomial, my function, my polynomial, equal to 0, and I'm going to try and solve for the x values by factoring. The first thing I notice is that each term I can factor an x out of. So let me factor that x out. I have x squared minus 2x plus 1 equals 0. And x squared minus 2x plus 1 factors rather nicely into x minus 1 times x minus 1, which equals 0. All right. I'm going to go one further step, which I'll need for the multiplicity step. I'm going to rewrite that as x times x minus 1 squared equaling 0. Okay. All right. Now, let's get my x values out of this. The only way x times x minus 1 times x minus 1 can equal 0 is if the first term, x is 0, or the x minus 1, either, both of them is 0, right? So there's one solution. And if I solve this guy, I also get x equals 1 as an x-intercept. It appears then that I have two x-intercepts, x equals 0 and x equals 1. So let me plot those. X equals 0, well, that's right there. And I've already plotted it by chance because the y-intercept happened to also occur at y equals 0, the origin. So a y-intercept at 0 or an x-intercept at 0 means you hit the origin. All right, so I've already got that point plotted. But I also have an x-intercept at 1. So I'm going to put a big red dot here at 1. Okay. All right, so I'm going to shift this over. So make sure you got everything down here. And then I'll head over to the multiplicities bit, which is the truly the new material for today. Okay, so I want to keep the graph on there. And now we're looking at the multiplicities of the x-intercepts. And I'm going to reproduce one step from the previous thing. I had that x times x minus 1 squared was equal to 0. That's where I sort of ended the algebra in the previous step. And I had two zeros. X equals 0. Remember, 0 is an x-intercept. And x equals 1. All right, this intercept, x equals 0, has multiplicity of 1 since x, how would I say this, x, I can think of it as x minus 0 to the first. When I factored my polynomial, I had an x to the first, not an x squared or an x cubed. So the multiplicity is the power on the factor that 0 came from. So this is multiplicity 1. X equals 1 has multiplicity of 2, since we had x minus 1 squared in the factorization. Okay, great. So what? Well, here's what we can do with these multiplicities. If multiplicity is 1, graph crosses x-axis at the 0 with crosses, no wiggle. All right, very technical term, no wiggle. That means if this is my x-axis, I either have something that crosses it from low to high or crosses it from high to low at that x-intercept, okay? All right, now x equals 0 has a multiplicity like that, right? So back over here, I'm expecting the graph to go through this x-intercept with no wiggle. So it's either going to come through like that or kind of come through like that, one or the other behaviors, all right? Hope you can see that. I'll try and be more thick when I go back through that thing, okay? All right. If multiplicity is 3, 5, 7, etc., the graph crosses x-axis at the 0 with a wiggle. So, like, if that is the 0, it might cross with a bit of a flattening and then up. Or if this was the 0, a bit of a flattening and then down, kind of like the graph of x cubed, okay? And then last but not least, what about multiplicities of even 2, 4, 6, 8? So if multiplicity is 2, 4, 6, some power, even power, then graph touches, but does not cross the x-axis at the 0. So if the 0 was there, I'm looking at touching the x-axis but not crossing, so diving back down. Or if the 0 was here, I could also touch it from above but not cross it and go back up there. So this is what the powers on the factors are telling us about what the graph looks like at those x-intercepts. Okay. All right. So let's try and, sorry, make sure you got that before I come back to finish up the picture. All right. So let's try and figure out what the graph's going to look like. I have to hit these 2 points. I have to hit my end behaviors. All right. And for x equals 0, that had multiplicity 1. So I have to cross the x-axis with no wiggle waggle, just straight cross, either from low to high or from high to low. Okay, one of those 2 things has to happen. Now, I have to hit this end behavior. So there's no way I can do this upper left to lower right, because if I did that, to go from there, this quadrant, down to this end behavior, I would have to cross the x-axis again. But there's no other x-intercepts. So that behavior cannot be correct. All right. The only way I can cross the x-axis there, nowhere to the left, and hit this is if I go that way and then join up with that. So I'm crossing the x-axis there. Now, x equals 1 had multiplicity 2. So that means I have to hit the x-axis and bounce back. Either hit it from above and bounce up or hit it from below and bounce down. Now, I am above the x-axis right before x equals 1. And the only place I get to hit the x-axis is right here. So it has to be that there must be like a turning point. And then I hit the x-axis and bounce up and head to my end behavior. All right. So the multiplicity tells me what the graph looks like just around that intercept, x-intercept. Straight crossing with no wiggles. And multiplicity 2 was a touch and bounce kind of behavior. And then I just have to think, okay, how can I do that and still connect up with my end behaviors? We will do another example at the start of class. I will do another example at the start of class where I talk through this procedure again, but have your notes ready and I'll do a more involved example at the start of class. Cool.